2.2 talks about the derivative of a function as a function. Well, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. The other definition will not work because the other definition reads f of x minus f of a. If you let x equal a, that will be an x. That will be a 0 automatically. So the definition of a derivative as a function in terms of x only works with the limit as h approaches 0 of f of x plus h minus f of x over h. Now remember, a derivative stands for multiple applications. One of them, slope of a tangent. Use the graph to estimate the values of each derivative. F prime of 0. So if I go to this graph and I sketch a line at 0, a tangent line. Now, we're not going to go exact unless we have the actual grid and measurements. We don't. But what do you think the slope of that line is? I'm going to say that's like a -4, -5, -6. Okay. How about B? F prime at 1. X equal 1. F prime at 1 is 0. How about F prime at 2? What do you think the slope of this line is? I'm going to say that's about a 1, rise over 1. How about F prime at 3? Isn't 3 a bit less? If this is 1, I'm going to say this is about a half. How about at 4? Okay, that's not a good tangent line. At 4, I'm going to say that's about a fourth. At 5, well, it looks like this is leveling off. I'm going to say that's like 1 over 5, 1 over 6. Sketch the graph of f prime. The important benefit out of this exercise, if this is f and I wanted to sketch a derivative, at 0 we have a -4. At 1 we have it at 0. Remember, this is the graph of f prime. At 2 we have it at 1. At 3 we have it at a half. At 4 we have it at a fourth. That's how the graph looked like. So, when the slope is negative, the graph is below the x-axis because that's just f prime. And when the slope is positive, the graph is above. The different notations throughout, oh, this is in the wrong place. So, this was Newton's notation. This was Leibniz. Differential equations, partial derivatives, and the definition. They write it in different forms to us. In this class, it's going to mean the same thing. Let f of x equal x cubed. Evaluate. Now, instead of doing this 4 times, why don't I find the derivative at x and then plug in x equals 0, -2, 10, and pi, and see how that works. Well, how do I find a derivative? F prime is the limit as h approaches 0, f of x plus h minus f of x all over h. So the derivative evaluated at x would be the limit as h approaches 0 of x plus h cubed minus f of x is x cubed over h, limit as h approaches 0 of x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. Limit as h approaches 0. Those cancel out. I'll factor an h out. When I throw 0 in for h, throw a 0 in, I got f prime of x to be 3x squared. Now I'll say, well, okay, now that I have this, let's go, okay, what just happened? Okay, something's not right. Okay, we're back to this. So now, this is what f prime is. When I say what's f prime of 0, that's simply 3 times 0 squared, which is 0. And you can guess it's very simple now to evaluate the derivative at many points as you like. 10 squared is 100, that's 300. And f prime, so instead of taking the limit and applying that 4 different times, it's easier to find the limit just once in terms of x and replace x by any value that you want, and this way you approximate the slope of the tangent of the derivative at all of these different points. Now, how can a function fail to be differentiable at a cusp? If you look at the cusp, the slope of the tangent, remember how that works? Eventually you'll reach a slope of a tangent that is undefined. Right? Before you go to the other part. A corner, a discontinuity, and again, if you look at the slope of the tangent, eventually you will get to a vertical tangent in which the slope is undefined. Now, if a function is differentiable at a, then it is continuous, right? The only statement that I can get out of that, if f is not continuous, then f is not differentiable, right? The negation of this, if a then b, the only true conclusion you could get out of that, if not b, then not a for sure. So, if a function is not continuous, automatically it's not differentiable. Very simple. Well, they're asking, the graph of a function is given. State the numbers at which the function is not differentiable. Support your conclusion. So, this is not differentiable at, and let's start with the first one, x equal -1. And why is that? Well, that's discontinuous. And x equal 0, that's not continuous. Here, x equal -2, let me fix that. X equal -2. And why is that? Because it's a corner. And x equal, oh boy, everything now is screwed. There. X equal 1 because it's not continuous. And here it's kind of hard to see x equal -2 because you have a vertical tangent. Kind of like right there. So, eyeballing this does help a lot. I have a problem that's a bit of a challenge, and since it comes up on the homework, I wanted to point it out. Given that f of x equals x to the 2/3, again, the same idea. Well, let's find the general formula for a derivative. That's the limit as h approaches 0, f of x plus h minus f of x all over h. That is the limit as h approaches 0 of the cube root of x plus h squared minus the cube root of x squared divided by h. The only way I can do this is if I clear the radical. And here comes the tricky question. Multiply by the conjugate. You're rushing. We multiply by a conjugate for a reason. If we take conjugates and we multiply them, we get rid of radicals. No, we get rid of square roots, because a square undo a square root. Here, what kind of radicals do I have? I'm looking at cube roots. If I want to get an a cubed minus b cubed, why am I looking for a cubed minus b cubed? Because a cube undo a cube root. Isn't that a minus b times the first squared, the last squared, and the product of those two? This is always positive. This is always the opposite of that. So the goal is not to multiply by the conjugate. The goal is to get rid of two squares if you have a square root. But we don't have square roots, we have cube roots. So the goal here is to get cubes. So I have to multiply, assume that this is this. What do I need to multiply it with to make it a perfect cube? I need to take the first and square it. I need to take the last and square it. And I need to multiply those. Not pleasant. Not something that you see a lot. This is always positive. This sign is always the opposite of that. Whatever you multiply the top with, you multiply the bottom with. Why is that? Because you're allowed to multiply by 1. Now, without even working it out, you could work it out. You have a lot of free time on your hand, right? This, I'm just going to copy. The top, I'm going to get the first cubed. If I cube the first, that will be x plus h squared minus the second cubed. There's the trick. And that's going to be the limit as h approaches 0. You know the drill. This is x squared plus 2xh plus h squared minus x squared over h times cube root of x plus h to the 4th plus cube root of x plus h squared, x squared, plus cube root of x squared. Those cancel out. If I factor an h out of that, 2x plus h and this h cancel out. If I let h equal 0, I'll get 2x over h equals 0 in there. I'll get the cube root of x to the fourth, I'm going to write this in 2 steps. A 0 in there, I'm going to get the cube root of x to the fourth and the cube root of x to the fourth. Why did that not? When you square it, that should be a 4. That would be 2x divided by 3 of those. That's 3x, the cube root of x, the x's cancel out. And finally, I got 2 over 3, the cube root of x. So that's my derivative. Now what? Now I would say, well, if you want to take f prime at 1, that is 2 over 3 times 1, which is 2/3. F prime of 2 is going to be 2 over 3, the cube root of 2. And f prime of 0, which is important, that is 2 over 0, which does not exist. And that is pretty much it for this section. That's all there is.